Now let's move on to our last and fourth example problem of chapter second lecture of chapter 8. Here we consider quite complex shaft system. The shaft system is driven by the motor M. Okay, and due to this motor M, shaft shaft AB is rotated at 480 RPM with constant angular velocity, which means that the energy input and energy output is balanced and no acceleration, and there is energy inlet from the motor 30 kilowatt, and there is energy outlet at G at H at G 20 kilowatt, at H 10 kilowatt, and the dimension is given as 60 millimeter radius, 80 millimeter radius here, and 160 millimeter radius here. Distance between gears are given as 200 millimeter equally, and the allowable shear stress of the shaft is 50 megapascal. So the problem asks us three questions. Question 1, torques and tangential force at gears and reactions at A and B, and compute minimum allowable shaft diameter. Okay, so given this allowable strength, what should be the minimum shaft diameter? If the shaft is too thin, it will be fractured. However, if the shaft is thick enough, it can sustain this much of rotation speed. Okay, so let's first solve torque and force problem. And to solve torque and force problem from the kilowatt, the power, we need P equals to be T times 2 pi F equation. Okay, so let's start from there. So the power is given as torque multiplied by 2 pi F or W, and F is given as the frequency 480 RPM divided by 6. RPM means rotation per minute, and 1 minute is 60 seconds, so you divide by 60 seconds, it's 8 hertz, like 8 rotation per 1 second. So if you plug this into the equation of P over 2 pi F, which is here, so at this point the torque must be 30 kilowatt by 2 pi F, becomes 597 Newton meter. Okay, and if you obtain the torque, and if you divide the torque by the radius, which is 160, it becomes 3.73 kilonewton. Okay, which is vertical direction. Now about the G point and C point, the torque is given as, I told you that this is 20 kilowatt energy outlet, so 20 kilowatt divided by the frequency 2 pi F, it becomes 398 Newton meter, and force is, you divide this torque by 60 millimeter, it becomes 6.63 kilonewton. And about the H, you have torque of 10 kilowatt divided by 2 pi F, 199 Newton meter. And about the force, you divide the torque by 80 millimeter and becomes 2.49 kilonewton. So with that, you can answer first question regarding the torque and force for gears. Then the problem asks us to find the reactions at A and B. So because there is a torque balance, the overall torque must be 0, such that there is no angular acceleration, and W, the angular velocity, is constant. So you don't need to worry about the torque acting on A and B. However, there should be some force, vertical direction or horizontal direction, to balance the force due to the gears. There is a force here, there is force here. So two force acts on the top part of the shaft, and the one force is acting on the side part of the shaft system. Okay, so this free body diagram draws the how the force is acting on. You can see that because the motor is rotating here, so this motor is pushing this gear downward. Okay, as a reaction, because this this gear want to rotate here, but due to the resistance here and there, there is no acceleration, so you can expect that force at C point and D point will be opposite direction. okay, opposite direction to the rotation direction. So this is how we draw the free body diagram: one vertical downward and two horizontal, but horizontal, deep down to the surface you are looking at. And about the A and B, we can have both horizontal and vertical force. So let's take y-axis and z-axis here. So we take this is by, ay, this is az and bg. Okay, so we have four unknowns. Okay, so regarding vertical direction force, yeah, fe and by and ay, yeah, you need force balance in vertical direction. Now let's consider the torque balance with respect to A, and let's consider torque in this direction. Yeah, torque in this direction. Yeah, then you have 3.73 multiplied by 600 millimeter clockwise, and this torque must be balanced by by multiplied by 80 millimeter. Okay, so and then this with this you can balance torque with respect to A point. Okay, so this is torque balance equation and force balance equation. Now let's consider force balance in horizontal direction. So AZ, BG, and FC and FD. So you have force balance along the horizontal direction. And about the torque balance, so with respect to A point, you have 200 millimeter multiplied by 6.63 and 400 millimeter multiplied by 2.49 kilonewton. This is 2.49, this is 6.63, and in opposite direction you have 800 millimeter multiplied by bg. Okay, and they should be cancel out each other. So after having 1, 2, 3, 4 equation, and we have four unknowns, we have 1, 2, 3, 4 unknowns, then you are guaranteed to solve this linear equation if they are independent linear equation, and these four linear equations happen to be the linearly independent, and we ends up having the four unknowns with some numbers. Yeah, ay, az, by, bg. So we obtained the reactions. And you don't need to worry about the rotation and torque at A and B, torsion at A and B, because you already have balanced power 30 kilonewton minus 20 kilonewton and 10 kilonewton at G and H. So due to the power balance, you don't need to worry about dissipation due to the torsion at A and B. Now let's move on to the third question. Third question asks us compute the minimum allowable shaft diameter. To obtain minimum allowable shaft diameter, you have to get the maximum shearing stress out of the system. To obtain the maximum shearing stress, you have to first locate where the maximum shearing stress would occur, and to do so, we have to draw a lot of moment and shear diagram. But let's solve this. So regarding the mg due to 2.8 kilonewton and 3.73 kilonewton at E and B, we can draw moment diagram here. Regarding this horizontal force, we can also draw my, the moment in this way as a function of distance. And regarding the torsion T, you can draw the diagram like this. Torsion at here and there, it's balanced out to be 0, but there is torsion within C and E section. Okay, so you can draw this moment diagram and torsion diagram as a function of position, according to our knowledge in chapter 4 and 5 and 3. Okay, so having obtained these reactions, mg and my, it contributes to normal stress along the x direction or the longitudinal direction, and the torsion T contributes to torque. Okay, torque and shearing stress. Okay, and combining normal and shear stress, you complete the Mohr circle and obtain the maximum principal stress and maximum shearing stress. And how can we do that? So we have mg and my component. Mg is this component and my is this component, and we have torsion T. And if you combine mg and my, because they are torque and they are vector, so you can combine them as large m vector. And the size of large m vector, because this is vector sum, is given as this. And this m vector give maximum torsion moment, maximum normal stress here and maximum normal stress here. And this torsion has the maximum shearing stress along the at the outside of this cross section. So you can expect that either that point or that point would give rise to the maximum normal stress and maximum shearing stress. And to obtain the maximum shearing stress, you need the largest Mohr circle. So you have to find the position with good combination of sigma m and good combination of tau m. The sigma m can be obtained by m times multiplied by c. C is the radius of the shaft. And I is simply the I for the circular cross section, and J is the J for the circular cross section. So and 2I is equals to be J. Okay, so because of this relationship, we have gone through this relationship in many lectures before. So after identifying this sigma m, tau m, so either that point and that point, you have sigma m, negative tau m for x. You have maybe 0 and tau m for y. So after identifying x and y in the Mohr circle and complete the Mohr circle, then what you can see is this radius of Mohr circle will give rise to maximum tau. Okay, so this maximum tau is given as this guy. Okay, R is simply you have one direction with zero normal stress. Even though we have normal stress here, we don't have normal stress in the opposite direction. So you have only one point that is that has a non-zero horizontal value, and the other point has zero horizontal value, and tau m is located here because tau m is occurring due to the torsion T. Okay, so after identifying this Mohr circle and try to represent R in terms of this Mohr circle, this is sigma m point, and this is average sigma, which is sigma m over 2. So this is sigma m minus sigma m over 2 squared plus tau m squared. And if you plug in the relationship mc over I and tc over j, and here and there, and identify then 2I equals to be j, you can write down maximum tau as c over j square root m square plus t square. So what you can see here is m square is simply mx square plus my square. So you can identify for each position A, C, D, E, B position, you can compute this value and see where this maximum tau max occurs, or where the radius of the Mohr circle is the largest. Okay, so out of the all moment diagram, we found that at this point, D point, it does not have largest mg, it does not have largest mi, but it has the largest t. But combining these three contribution, you happen to have the maximum tau max, or maximum square root mi square, mg square, and tau square. And after plugging in the numbers at D point, you have 1357 Newton meter for this square root value. And what you can identify is that this must be smaller than allowable stress, and this is the same as what is it, like c over j, and the square root value. Okay, so after plugging in the square root value here, and the c is our unknown, and j is we can obtain from the j from the c. J is pi over 2 c to the cube, and tau allowable is given as 50 megapascal. Then you can solve this equation for c, and c turns out to be 25.85 millimeter. This is the radius value after obtaining the radius. if you do multiply 2, if the diameter becomes 51.7 millimeter. So diameter should be equal to or larger than 51.7 millimeter to sustain the maximum shearing the shearing stress due to 30 kilowatt rotation or 480 RPM rotation of this shafted system. Okay, so here you can see from this chapter, this chapter combines all the knowledge. So yeah, even though you have taken midterm, to do a good job in final exam, you have to I would say study again the contents before midterm, so that you can draw this moment diagram and torsion diagram without difficulty. And after combining all those stuff in very nice geometrical sense without any mistake, then you have to locate where the maximum shearing stress or principal stress occurs. And after identifying this, you have to do accurate calculation without mistake to obtain the final answers. Okay, so yeah, this is quite demanding, and it's not easy to perform all those calculations. However, what can you do? Yeah, this we learned all these knowledge to do these kind of analysis, and this chapter somehow gives you nice finale, right? So you apply all the knowledge you have learned from the freshman physics and ME231 until the midterm, and even after midterm you learned the new knowledge, and combining everything, now you can determine whether the structure is reliable or not if somebody gives you the loading mode and the strength of the material. Okay, so hopefully you started to find that this course is meaningful and useful for determining the structural safety in a big picture. By making very nice design, you can save life of people, a lot of people's life, right? If you don't design your structure or car in a appropriate way, yeah, you're gonna somehow cause like a death of a lot of people, right? You've seen that examples in collapse of buildings in Korea or America and other cities in the other countries. And hopefully this chapter gives you some idea on how to apply the knowledge. Of course, in realistic and professional design of the structure, we're gonna rely on the computers, because the geometry will be really complex, and it's not easy to do hands-on calculations. Yeah, you have to use numerical technique called FEM, finite element analysis, and you can also take some introductory course in undergraduate level, and you can take the advanced course in graduate courses. Okay, so with that, let me finish the recording for the final video of today's lecture.